Hi. Welcome back. In today's class, we will be learning Introduction to Statistics for Data Analysis. In this class, we explore the fundamentals of statistics and its role in data analysis. Statistics forms the backbone of many analytical techniques that help us make sense of data, draw conclusions, and make predictions. The class focuses on key statistical concepts, including descriptive versus inferential statistics, probability and hypothesis testing, regression analysis, and the distinction between correlation versus causation. By the end of this class, you will be able to understand the difference between descriptive and inferential statistics. Learn about the concepts of probability and hypothesis testing and how they help in data analysis. Understand regression analysis, linear and logistic, and how to apply it to real-world problems. Grasp the important distinction between correlation and causation. Descriptive versus inferential statistics. Descriptive statistics. Descriptive statistics is about summarizing and describing the features of a dataset. The purpose of descriptive statistics is to organize and simplify data so it can be easily understood. Common measures include measures of central tendency. These include mean, the average of a set of values; median, the middle value when the data is ordered; mode, the most frequent value in the dataset; measures of dispersion. These tell us how spread out the data is. Common measures are range, the difference between the highest and lowest values; variance, a measure of how far each data point is from the mean; standard deviation, the square root of the variance, showing how spread out the numbers in the dataset are. Visualizations, data can also be represented using histograms, bar charts, and box plots to give a better understanding of its distribution. Inferential statistics. While descriptive statistics focuses on summarizing the data at hand, inferential statistics allows us to make predictions or inferences about a larger population based on a sample of data. The key concepts in inferential statistics include sampling, collecting data from a subset of the population rather than the entire population; confidence intervals, a range of values that is likely to contain the population parameter with a certain degree of confidence; hypothesis testing, a statistical method used to make inferences or draw conclusions about population parameters based on sample data; probability and hypothesis testing. Probability. Probability is the measure of the likelihood that a given event will occur. It ranges from 0 to 1, where 0 indicates an impossible event. 1 indicates a certain event. Probability is foundational to understanding how data behaves and to making inferences about populations. Basic concepts include events, a single outcome or a set of outcomes from a random experiment; conditional probability, the probability of an event occurring given that another event has occurred; Bayes' theorem, a mathematical formula used to update the probability of an event based on new information; hypothesis testing. Hypothesis testing allows us to make data-driven decisions by evaluating assumptions about a population. It typically involves two hypotheses. Null hypothesis, H, the hypothesis that there is no effect or relationship; alternative hypothesis, H, the hypothesis that there is an effect or relationship. The steps in hypothesis testing are: set the hypotheses. Choose a significance level, alpha, typically a value like 0.05, which represents the probability of rejecting the null hypothesis when it is actually true. Collect data and calculate the test statistic. Make a decision. If the p-value, probability of obtaining the observed result, is less than the significance level, we reject the null hypothesis. Regression analysis, linear and logistic regression. Linear regression. Linear regression is used to predict a continuous dependent variable based on one or more independent variables. The relationship between the variables is modeled as a straight line, given by the equation y equals beta 0 plus beta 1x plus y equals backslash beta underscore 0 plus backslash beta underscore 1x plus backslash epsilon. Where y is the dependent variable. Xx is the independent variable. Beta 0 backslash beta underscore 0 is the y-intercept. Beta 1 backslash beta underscore 1 is the slope of the line. Epsilon backslash epsilon represents the error term. Linear regression helps in understanding relationships between variables and making predictions. For example, predicting a person's weight, dependent variable, based on their height, independent variable. Logistic regression. Unlike linear regression, logistic regression is used when the dependent variable is binary, e.g., yes/no, true/false, win/lose. It models the probability of a certain class or event occurring, using the logistic function, sigmoid curve. P, y equals 1, equals 11 plus e minus, beta 0 plus beta 1x, P, y equals 1, equals backslash frac, 1, 1 plus e caret, dash, backslash beta underscore 0 plus backslash beta underscore 1x. Where P, y equals 1, P, y equals 1 is the probability of the event occurring. The rest of the equation follows the same format as linear regression, except we apply the logistic function to predict probabilities. Correlation versus causation. Correlation. Correlation refers to the statistical relationship between two variables. It shows how closely the variables move in relation to each other. It's measured using the correlation coefficient, R, which ranges from -1 to 1. +1 indicates a perfect positive correlation, both variables increase together. 1 indicates a perfect negative correlation, one variable increases while the other decreases. 0 indicates no correlation. However, correlation does not imply causation. Just because two variables are correlated doesn't mean that one causes the other to change. Causation. Causation refers to a cause and effect relationship between two variables. In other words, one variable directly influences the other. Establishing causation typically requires controlled experiments and other techniques such as regression analysis to account for confounding factors. The classic phrase correlation does not imply causation is a reminder to avoid jumping to conclusions about cause and effect relationships based solely on observed correlations. Conclusion. In this class, we covered some essential statistical techniques and their application to data analysis. The difference between descriptive and inferential statistics. The role of probability and hypothesis testing in drawing conclusions. How to use regression analysis, linear and logistic, for prediction and classification tasks. The key distinction between correlation and causation, emphasizing the importance of not jumping to conclusions about cause and effect relationships. By mastering these concepts, you will be well equipped to make informed decisions based on data and understand the deeper statistical principles behind data-driven insights. Thank you for listening. See you in the next class.